Last video we have discussed about insect outbreak, and finally we have arrived at an equation in the dimensionless form, right? And we have reduced in the 4 parameters into just 2 parameters, okay? And in this video what we are going to do is we are going to do the analysis on this equation. So the first thing which we do as an analysis is calculating the fixed point, okay? And in order to calculate the fixed point, I have to equate this to 0 or this to 0, and I have to do the analysis. But the equation doesn't look simple to make an analytical solution for the fixed points. So what I'm going to do is I'm going to consider this part as g1 of x, okay, and this part as g2 of x, and I'm going to plot these two functions, and wherever they intersect, those are the fixed points, okay? So that's what I'm going to do. So if I plot those two things, okay, so if I plot those two things, this is what I will get. So this is my x-axis, okay, and this is my function g1. No, that's not a function g1. I can reduce this equation further. If you see in this equation as well as in this equation, x is common, right? So from that I could say one of the solution is 0, okay? So actually x into g1 of x is what this one, okay? So basically what I'm going to do is I'm going to plot this term divided by x, and the same thing for this one as well, okay? So what is g1 of x? That is r into 1 minus x by k, and g2 of x is equal to x by 1 plus x square, okay? So let's plot these two things and see where they intersect. So this is g1 of x, okay? Actually here I have scaled my y-axis slightly, okay, to have a good plot, to visualize the plot properly, okay? And this is my g2 of x, okay? The reason it's having this particular form is because of the following reason. So if we see this is the term for very small value of x, okay? For very small value of x, the denominator is going to act like just 1, because this is going to get ignored. So at that time I can approximate this function as just x, okay? Therefore it's showing the behavior like this, okay? And for a very large value of x, okay, then this term is going to dominate. If that's going to dominate, I can approximate that as this whole term is x by x square, which is 1 by x. So if it's 1 by x, then it will approach to the x-axis asymptotically. So that's what we observe over here. So in between those two curves will meet and come back to x-axis. So that's why we have this curve in this particular shape, okay? Now if we see the point where g1 and g2 meet, okay, so that is this point. So we already have one point which is this point, that's a fixed point. In addition to that, we have this point which is another fixed point. since this is an unstable fixed point, okay, so therefore we will have this as a stable fixed point. Okay, now we have two parameters, one is r and another one is k. Okay, so what is this r and what is this k? So let's revisit those two parameters once again. So what is the meaning of this r? R is equal to capital R A by B. Okay, and this k, small k, is equal to capital K, okay, by A. Okay, so here if we see this r, that term small r is proportional to the birth rate of that insect, and not only that, it is also proportional to 1 by B. So what is B? B is the that saturation value of the reduction of the insects due to the predators, right? So if that decreases, then this value is going to increase. Okay, so it not just depends on this capital R value, but also depends on this B. Okay, and if you see here, this K is proportional to this capital K, where this capital K is actually a carrying capacity for this insect, and that's going to go up if the number of trees are going to go up. So basically, if the number of trees are going to go up, my small k value is going to go up. Okay. Okay, so with this understanding, let's go back to the curve again. So now the system has some r value and some k value, which means some number of trees. Okay, and this insect has some number of birth rate, and for that case, if the number of trees are the insects are very less, okay, so the number of trees are going to go up. Okay, because there aren't many insects to kill those trees. Okay, so it's gonna go up, and nothing is going to change. Okay, it's gonna keep on increasing, and if you see, this is the only point where it intersects, and there isn't much increase in the insect. Okay, but if this r values, let's say slightly more, maybe like 2.57 value, now say this is going to be the equilibrium point, which means this is going to be the number of insects. Okay, now what I'm going to do is I'm going to increase the k value, which means I'm going to increase the the number of trees are going to get increased. So if that's going to get increased, okay, because of the less number of insects to kill, okay, and it's keep on increasing, okay, and at one point, if you see, we are having not just one equilibrium point or two equilibrium points, we also have two more equilibrium points, right? So if we have two more equilibrium points, what about the stability? The stability is actually this equilibrium point is still going to be a stable equilibrium, because this equilibrium point will always be unstable. Okay, so this is a stable equilibrium point, this is an unstable equilibrium point, and once again this is a stable equilibrium point. But since earlier this was the population, so it will just track to this equilibrium point. The system will go towards this equilibrium point and not to this equilibrium point. Okay, So still we have less number of insects, so there is no problem to for the trees to grow further. Okay, so the number of trees are going further, increasing further, and at some point, if you see, look at this point. Okay, look at these two equilibrium points. Okay, so those 2 points are collide each other and got vanished. Okay, has got vanished. And if you see, now the system is having only one equilibrium point, which is this. What does that mean? So it means when the system goes from some value near to 8.6, okay, when it crosses, then actually this is the only equilibrium. So suddenly there is a very large increase in the number of insects. Okay, very large increase in the number of insects. Now this is the number of insects. Okay, this is what insect outbreak. And now what's happening is because of the very large number of insects, it started eating more trees. So now this k value, which is almost 10, now it's going to go down. Okay, it's going to go down. So if it go down below 8.8 around something like that, once again we could observe these two fixed points, addition to this fixed point, right? But the number of insects will not suddenly decrease to this value. Okay, because this is a stable fixed point and this is an unstable fixed point, and then this is a stable fixed point. But the previous amount of population is somewhere near to this value, therefore it will stick to this equilibrium point. Okay, so which means the number of insects are still more even after the value of 8.7. okay, so the number of trees are further gonna go down. Okay, so it will keep on going down. Okay, and maybe after around, yeah, if you observe this fixed point, okay, this fixed point and this fixed point, okay, and they approach together and they collide and they got vanished. Okay, so it happened something around 6. Okay, so earlier it was 10. Okay, now it started getting reduced to 6. At that time the number of insects will reduce drastically and it will go to this value, like I don't know, so this value less than 1. Okay, yeah, 0.841. so this is what the cause of this insect outbreak. So it was the trees were having like 10, okay, that has got reduced to around 6, right? So like what to say, out of 10 trees, 4 trees have gone. So such a big deforestation happened because of this insect outbreak. Okay, so this is what has been analyzed by Ludwig and his group. And also if we observe that, we could observe that hysteresis behavior, because now this is the fixed point, and suddenly after this point, for this value of k, I am having this as the equilibrium point. Now if I reduced back, I am not suddenly jumping over here. Okay, I am slowly moving this value, and only here I am having this jump. Okay, so this is also a good example for a hysteresis behavior and also for a catastrophic behavior. Okay, so Right, so that's the story about an insect outbreak. And in the book they have also discussed about how to calculate the bifurcation curve, okay, and what range of R and what range of K we could observe this outbreak scenario, and what range such a thing will not happen. So those discussions are in this book, and I leave that as a reading exercise. Okay, so with that I would like to conclude this topic. Thank you.